Okay, this is a second part of week 3, and this will go into week 4. We're going to be talking about our raster environments, and then we're going to be doing two very basic raster analyses, geoprocessing analyses, and that is analyzing distance and density. There will also be some other pieces that come out of that are normally part of it. But what I want to talk about today in our overview video is the idea of examining a raster data set to see really what we can see about it. Remember, when we look at a vector data set, we look at its coordinate system, and then we begin to look at its attribute table, and we see what attributes are stored with it, when we see very quickly that it's point, line, or polygon. Well, when we look at raster data sets, it's a little bit more complicated in terms of understanding what they are, and so we'll go through that. Then, very briefly, we're going to talk about visualizing raster data sets. And in the exercise, please remember about the ideas of layer files and transparencies. I'm going to give some basic things today in this general video, and then we're going to touch on those in terms of applications. And then again, I'm going to very quickly introduce the ideas of distance and density as it relates to raster geoprocessing. So first of all, anytime that we're looking at a raster data set, when we load that into ArcMap or ArcPro, and by the way, this really doesn't apply to Arc Online. You will look at raster data sets in Arc Online, but they're served out very differently. They're often treated as image files, and so it's a different environment, and that's really the purview of an advanced GIS class. But in either ArcMap or ArcPro, just like in a vector data set, we're going to right-click on the feature class, and we're going to open up that properties dialog. And here you see it for ArcMap, and what you'll notice is that under source, and this is true again, ArcMap, ArcPro, we're going to look at a couple of very important aspects. And in both of them, you'll notice that it's going to have under properties these headings. And in the first case, we're going to be looking at raster information. And there we're going to see a couple of important ideas. First of all, we can see the general size of the file here by its columns and rows. And that, again, literally means how many columns across and rows up and down that we have. So again, it's kind of its X by Y. The next piece, though, that we need to know is how big are the pixels. And so here we see cell size, X and Y. In this case, they're square, and most of the time that will be the case, although it's not always the case. What we will notice here then is this other aspect in raster information, which is pixel type and depth. And what we need to understand here is whether or not our data is being stored in a complex form, really, or a simple form. You may see here 8-bit, and you'll either see that as signed or unsigned. Well, 8-bit unsigned would mean that the pixel can store the values between 0 and 255. That would be a very basic 8-bit positive storage. If we saw that it was 8-bit and it was a positive and negative, or signed, then we would be able to store, again, it's still going to store 256 values, but that would mean that we would store between negative 128 and positive 127. And so that's often for things that we think of in terms of colors or in terms of categories of data. If we have numeric values that are complex, in other words, they're decimal places and they're positives and negatives, then we tend to store those as floating point 32-bit. And what that simply means is that we can store an incredibly complex level of data. So again, floating point means it has a decimal place. And in this case, floating point 32-bit means that it's positive and negative. And in this case, it can store literally 3.4 times 10 to the 32nd, or I'm sorry, 10 to the 38th values. So an immense range of values. And if you think about that, we might have 8 places past the decimal point and then billions on the other side, and that would allow us to store that level of data. Now the next piece that we might see, I think I went one too far here, would be the spatial reference information. And again, it's very important in working with raster data sets, especially with raster data sets, that we have typically projected data, and in this case we have 2 units that are important. First of all, we have linear units, and that helps us understand that 30 by 30 we saw before. That means it's 30 foot by 30 foot for each pixel. And then our angular units And this means that even though it is projected data, we understand the projection as using degrees. Again, that's fairly standard. The last thing that we may look at in terms of our raster data set, and there's lots of pieces here, would be the idea of its statistics. Okay, and so again, I'm sorry. When we look at statistics, what we're going to see then is the values, the range of values that are present in a band. And in this case, since we only have one band, this shows us the elevation data has a range of 122.67, etc., to 749. And so that's our feet. And this is what our data shows. In attribute data for categorical data, we might see frequencies. But again, this helps us kind of understand what our raster data is all about. Now, in a Arc Pro environment, same idea. I just want to point out that the interface is a little bit different. You're going to click on source, and then you'll notice here those same ideas we just talked about: raster information, band metadata, and then statistics and spatial reference. All of those, we simply click on them and they'll expand. Okay, so that's how we see the properties of a raster data set. Now, raster visualization is another piece of this. Raster data, because it has a value in each pixel, we have to decide how we're going to view it. And at least for this class and the data that we're going to be looking at, we're simply going to use two options here. One of which is classified data. That is, we put each pixel into a class or a range of values or categories. And so in this case, for example, we have elevation data. But what I've done here is I've said I want to put it into, and you'll see right here, I'm going to click on symbology, and then we would say the number of classes is going to be 10, and I want it to be in an equal interval. And of course, that makes sense for raster data. That is elevation. We want each of these intervals to be equal. And so you'll notice that it is, in fact, in colors. It is always important when looking at raster data set and doing it in a classified visualization to understand the number of classes. Greater the number of classes, the more fine your data is, but again, makes it a little bit sometimes harder to read. And then the classification method here, again, equal interval, natural breaks, standard deviations, or even quantiles could be used here. But again, think about what you want it to say. Now, what that would look like is almost kind of like a contour map, in this case, of our elevation data. And so we can see there are classes, and we can see the colors, in fact, forming almost our contours here. Now, what is important in raster data also is that we might use something called a stretched visualization. And what this does is provides a continuous range of colors across the data values without any breaks, in other words, without any categories to them or classes, and we simply stretch it. What this does is it allows us to see continuous variation because we have continuous data. Stretch classification or stretch visualization, should only be used for continuous data. The other thing that you're going to see here is something called a hillshade effect, and you'll notice it right here. And what that does is it uses the values to create, in a sense, a three-dimensional aspect, and then it casts a shadow from them. Let me show you what that does. It doesn't do anything in terms of analytics, but it does improve visualization. So, for example, here is our data stretched across its values, and you'll notice that it's the same data that we looked at classified, but we can see much greater variation across some of these areas that are lost when we classify the data. Now, the problem is that we kind of lose information here. It's hard to see really what's going on when our values come very close together. And so by adding the hillshade effect, we actually begin to see the topographic characteristics of our data. And so sometimes that helps. Sometimes in these are very bright colors, it can be somewhat confusing. Okay, last thing I want to point out in this, again, I'm just going to briefly introduce the ideas of distance surfaces, and then we're also going to look at density surfaces. So we're going to be doing both of these. Our distance surface, unlike our buffer, although it may look, when classified, very similar to it, what this actually is doing is for any source, and again, we're going to use our points as sources, the distance tool and distance geoprocessing in raster gives each pixel the least distance from a source location. And so for any pixel, we calculate, so again, for this pixel, for example, we calculate its straight line distance, center of pixel to center of pixel, based on the change in x and the change in y, that is our legs, and we can then calculate the hypotenuse. That is what is assigned to each pixel. The challenge with Euclidean distance then is, well, which source did it come from? So if I look at this pixel right here, where did it come from? Well, we answer that by the two other pieces that are typically generated, and that is by our direction. And so for each pixel, it will also tell us the direction to the source that that distance was calculated for. The other thing that we can then do is very much like a Thyssen polygon, is our allocation. So not only do we know, in this case, the distance for, let's say, this pixel, we know what direction back to its source. And then if we come over here, we can say, well, all of these pixels went to this source. And so in distance, we typically end up with 3 raster data sets that help us understand distance. Euclidean, true Euclidean distance, then Euclidean direction, and Euclidean allocation. All right, point density. And then we're going to be using the simplest one. And in our point density exercise, all we're going to be doing is a basic point density, as opposed to in advanced JS, we're going to be talking about kernel densities and higher levels of densities. But the simple idea is densities essentially predict or estimate for any given pixel the number of points that would likely fall inside it. Now, the pieces that are important is how far do you look out? In other words, a point density doesn't actually look at the entire area that you're looking at. It looks out a given range of distance. In other words, in a simple, and you can actually see the output here, you're only going to look out so far to look for points because you don't really want to calculate all of them. The next thing that we're going to talk about, and again, we'll do this on Monday, is the neighborhood. That is kind of what's the shape that our search goes out in. Normally it's a circle. But then we also have to say, well, what is my result? What is my cell size that I'm going to put the information into? And lastly, of course, our area units. Is it how many points per square mile, per square kilometer, per hectare, what have you? Okay, so those are the basic point density. And again, we have inputs of points and then a concentration, a way of estimating the count of those per unit area. All right, so given that, the next videos will walk you through these tasks. And again, our tasks are going to be to use the point direction, or I'm sorry, yes, the point distance tool, and then we're going to be using the point density tool, and we'll be using that to do some very basic questions. First of all, we have some cell towers in our study area. We're going to see what the distance is to them, and we're going to then get our distance, direction, and allocation rasters for that, and then we're going to do a very basic point density for automobile accidents, and we're going to compare those densities across a couple of fields. We're going to look at how does January and July differ in terms of accidents, and then we're going to look at accidents that are related to alcohol versus not, and see if their densities are different. Okay, that's it. We'll pick this up in the example videos on how to do each of these tasks.